Here we're going to have a look at the reactivity of benzene. And remember that benzene has got the following structure. And because of the delocalized electrons above and below the plane of the ring, we say we've got a region of high electron density above and below the plane of the ring. Remember, there are 6 electrons in this extended pi network. Because you've got a high region of electron density above and below the plane of the ring, this will attract electrophiles, just like the carbon-carbon double bond in an alkene. So remember when we looked at alkenes, we said that they attracted electrophiles, something like HBr. And remember we said that we get a mechanism that starts off looking something like this. So we looked in alkenes at this carbon-carbon double bond being a region of high electron density, and that therefore attracts electrophiles, that is species which can accept a pair of electrons, and these species usually have a positive charge or a delta positive charge. Now, benzene, we say it attracts electrophiles. The electrophiles we'll be looking at in benzene will actually be electrophiles with a full positive charge. They're examples we'll look at of the electrophiles, the ones with a full positive charge. The reason for this is that benzene is far less reactive than an alkene. So we need a more powerful electrophile. Instead of one with a delta positive, we need one with a full positive charge. It's worth mentioning that benzene and compounds of benzene would not react with nucleophiles. So imagine I've got something like this molecule here, and we may think that this will react with a nucleophile such as ammonia in a nucleophilic substitution reaction. Now I would say if this delocalized ring system wasn't here, then that certainly would react in a nucleophilic substitution reaction. However, because we've now got this high region of electron density above and below the plane of the ring, this will prohibit nucleophiles attacking the ring. Why is that? Because this lone pair here is repelled by the region of high electron density above and below the plane of the ring. So, nucleophilic attack on a benzene ring would be prohibited. So, this reaction here, this attack here, would be a no-go. So, the first thing we've looked at then is why benzene attracts electrophiles and why it repels nucleophiles. Now, benzene will react in such a way where it will try and retain the delocalization stability. And the only way it can do this is if it reacts with the electrophiles in a substitution reaction. So what we get then is that the electrophile actually replaces the hydrogen in the benzene ring. So we actually undergo a substitution reaction. If an addition reaction was to take place, so let's just have a look at one of the products if we had an addition reaction. what we would get there is that 2 of these 6 electrons in benzene would actually now be in this carbon electrophile bond, which means then we'd only have 4 electrons delocalised in this ring structure. And this molecule, therefore, is going to be far more stable than this molecule. Why? Because this molecule here has got 6 electrons delocalised. This molecule here has only got 4 electrons delocalised. The more delocalised electrons we've got, the more stable it is, the more the charge has been spread around. So here we've got 6 electrons. Here we've only got 4, and the other 2 are in this bond. So these 2 electrons are now not delocalised. It makes it less stable. Therefore, when benzene reacts, it will always favour substitution reactions. That brings us on to the mechanism, the general mechanism of benzene. And the name of this mechanism is electrophilic substitution. And we've explained earlier on in this video why that is. Why does it attract electrophiles? And why does it undergo substitution? We've mentioned that here. The general mechanism then is as follows. The high region of electron density then attracts an electrophile, and we're going to be looking at 2 specific electrophiles in our A-level course. And what happens is that 2 of these 6 electrons are used to form a new carbon electrophile bond. That gives us the following intermediate structure. And this is going to have a positive charge, this structure, and that positive charge is delocalised. It's sort of spread around some of the carbons in the ring. Now, the 2 of these electrons that were in this ring are now bonded to this electrophile. But in order to retain the delocalisation stability, it wants to get 2 electrons back. And it gets them 2 electrons back from the carbon-hydrogen bond. So the carbon-hydrogen bond breaks. The 2 electrons that were in this bond are then given back to the ring, and that kicks out a H plus ion. A key thing to remember about this intermediate structure is that this horseshoe, as we call it here, must not extend beyond, if we label these carbons 1 through to 6, it cannot extend beyond carbons 2 and 6. So this horseshoe must not extend beyond carbons 2 and 6. And that will also then give me a hydrogen ion. And that there is my general mechanism for electrophilic substitution. What we'll look at in some later videos is specific examples of what these electrophiles are, and just as importantly, how we generate these electrophiles. And that there is the general reactivity of benzene. And in this video, I've explained why it's electrophilic substitution, why it attracts electrophiles and not nucleophiles. I've also explained why benzene reacts in substitution reactions and not in addition reactions.